50% of the teacher's desk is covered in exams. What's the probability of spilling coffee on one of them? Half and half. Get it? And I do like half and half in my coffee. So we're going to be looking at independent and dependent events today, and we're going to start with compound events, which is basically more than one event happening. And one good way at looking at these is to make a tree diagram. I sometimes say a sample tree. So we have an urn with 4 marbles, 2 red, 1 green, and 1 white. We're going to make a tree diagram to determine the outcomes of drawing a marble, replacing it, and then drawing another marble. So notice that I am replacing it here. We're not going to worry about dupes, and I'll show you what I mean by that. So first of all, for the first marble, you could get red or the other red marble, the green and the white. And the reason I'm double listing the red, it makes our life a little easier right now because each one of these is equally probable. All right. So let's say I draw the red and put it back in. What could I draw on the next one? The same 4 marbles. And that goes on for all of them. So I have a tree diagram with 16 different outcomes. Red, 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 green, red, white. And I could keep going, and that is all of the outcomes. This would be the sample space for this, including the dupes, where each one of these is equally likely. So with the dupes, how many outcomes are there? There are 16 equally likely outcomes. How many outcomes had a green marble first and then a red marble second? Well, there were only 2 that had that. A green marble first and a red marble second. These 2 right here. Now, what is the probability that you draw a green marble first on the first draw? That would be basically 1 out of 4. And what's the probability you draw a red marble given that you drew a green marble? Well, let's say when the given means that I know this happens. So I'm not going to worry about this point and before. What's the probability of getting a red? Well, there are 2 ways to get a red out of 4. So it's 1/2. Then the question is, what is probability he draws a green marble and then a red marble? So the green is not given anymore. The question is, what is the probability of getting these 2 outcomes, green then red, out of the whole thing? Well, one way I could say is there are 2 outcomes out of 16, which is 1/8. But if you multiply these 2, what do you get? 1/4 times 1/2 is 1/8. Probability of getting a green on the first, 1/4 times 1/2 is 1/8. Now let's change up the situation, and instead of putting the marble back, I'm going to keep the marble. So what that's going to do is that's going to change some of our probabilities for the second draw. For the first marble, it should be the same, 1/4, 1/4, 1/4, 1/4, because all the marbles are there. But what's going to happen now is if I draw a red there, it's going to remove that option. If I draw this red, it moves that option, removes that one. The green is no longer possible here, and the white is no longer possible there. So how many outcomes had a green marble first and then a red marble second? It's 2 outcomes still. So this time we have 2 out of 12 instead of 2 out of 16. And you can see here are the 12 outcomes from the sample space. That's 1/6. Now let's go back and look at the probability of drawing a green marble on the first draw. That's not different. That's 1/4. All right. What's the probability that you draw a red marble given that you draw a green? Well, there are only 2 outcomes here out of 3. So it's actually 2/3. So the probability in this scenario is actually going to be, if we tried multiplying it together, 1/4 times 2/3, that would be 2 over 12. Which is 1/6. So you can see that the probabilities when we don't replace changes from the probabilities when we did. So there's conditional probabilities. This red is dependent on the green. And the way I read this right here, see that probability of red given green. That vertical line there means given. Okay, so if A and B are independent, that means they don't affect each other, then their probabilities do not affect each other. Therefore, that would mean that the probability of A given B is just the probability of A. B doesn't affect it. And the probability of B given A, well, A doesn't affect it, so it's just probability of B. Events that occur without replacement are usually dependent. So you saw how our probabilities changed when we kept the marble. We didn't put it back and replace it. So what kind of events are dependent? We'll look at these 4 here. Drawing a marble from an urn, replacing it, and drawing a second marble. That's the first example we saw, and that was independent. Rolling a die and then drawing a card. Those do not affect each other, so they're independent. If I draw 2 marbles from an urn and keep it, that would be dependent. Rolling a die twice, the first roll doesn't affect the second roll, so that should be independent. So our answer in this case is C. Now, the probability of 2 or more events occurring is a product of the events. This is also known as the multiplication rule of probability. So the probability of A and then B is just the probability of A times the probability of B. This symbol right here means and, so that we get A and B. You might sometimes say and then. It depends on the wording of your problem. Now, rolling a die and flipping a coin. Are the 2 rolls independent or dependent? Or, well, is the roll and the flip independent or dependent? And they're independent. So what's the probability of getting a 5 and heads? So I would write it, probability of 5 and heads is the probability of getting a 5 and then the probability of getting a head. So I'm doing it in that order. So it would be 1/6 times 1/2, which is 1/12. You just multiply the probability, so it's pretty easy. Now let's revisit that survey on cats and dogs. So let me go ahead and fill in the totals. I changed these to probabilities. So we could say 0.6% of the people like cats and like dogs. 0.2 don't like cats, but they do like dogs, etc. So I'm going to go ahead and fill in these totals. What is the probability a student likes cats and dogs? So again, I had just said it, but cats is this column right here, and dogs would be this blue row right there. So the probability a person likes cats and dogs is the number that falls into both, 0.6. Now, can we just multiply the probability of liking cats times the probability of liking dogs to get that 0.6? Well, the probability of liking cats is 0.72. The probability of liking dogs is 0.8. When I multiply those two together, I don't quite get 0.6. And why is that? Well, these two are not really independent. There's an association between them. So let me introduce the idea of a given again. Remember how we said given that we drew a green marble, what's the probability of getting a red? Well, given that a student likes cats, what is the probability they like dogs? So in the tree diagram, we only looked at the green branch. So what we're going to do now is we're only going to look at the like cats column. This right here is our entire world, the yellow part. Now, does our world add up to 100%? It doesn't. So how are we going to figure this out? Well, we're going to say the probability of liking dogs given cats is the probability someone does like dogs and cats. See that right there? Over the whole world there. So if I add up these totals, I get 0.72. And that gives me 0.833. So that is a conditional probability of liking dogs given that you like cats. Now let's just go ahead and multiply the probability of cats, which we said was 0.72, times this probability that we like dogs given we like cats. So that would give us 0.6. And what does that match? That's a probability of cats and dogs. So when I change from probability of dogs to probability of dogs given cats, it worked. And that's because they are not independent. I have to do a conditional probability. See the 0.8 there is probability of liking dogs in general. But for this to happen, that they like cats and dogs, these dogs, people who like dogs also have to like cats. So we actually want that number right there. Okay, so this gives us the revised multiplication rule. Probability of A and B is the probability of A times the probability of B given A, because we need to make sure that A will happen after our probability of A. And you can always use this version instead of probability of A times probability of B, since probability of B given A is just the probability of B if they're independent. So if we know the probability of B and the probability of A given B, we can actually work backwards on that multiplication rule, and we get this formula. So basically, I had rearranged it. That probability of B goes there. And if you look on the math chart, the formula chart you get to use on your AP test, it's right over here. So it's in section 2 on the formula chart. There are only 2 formulas there. It's the second one, and we covered in the last lesson the first one. So let's go ahead and look at an example. Now we're going to just start using the formula. Miss Bombardella teaches both geometry and pre-cal. The probability that the student had Miss B for geometry is 0.18. The probability that the student had Miss B for geometry and for pre-cal is 0.03. What is the probability to the hundredths that a student will have Miss B for pre-cal if they had her for geometry? So, probability of geometry is 0.18. Probability that they had her for both geometry and pre-cal and geometry is 0.03. So the probability of getting pre-cal, given they had geometry with Miss B, is the probability of pre-cal and geometry over the probability of geometry. In this case, it's the 0.03 over the 0.18, or about 0.167. Let me go ahead and draw a Venn diagram for that. So we have geometry, we have pre-cal. Both together is 0.03, which means, and I know that the probability for geometry has to add up to 0.15 for this, 0.18 for this circle, so that means this has to be 0.15. So it doesn't hurt to see a Venn diagram and how that all works out. The better you are with Venn diagrams, the easier probability will be for you. Now, speaking of which, let's revisit some more Venn diagrams. So the probability that someone is out of dress code, that would be this circle right here. It would include both pieces, the 0.006 you see there and the 0.045 that is in the overlap. So that probability that a student is out of dress code is 5.1% or 0.051. All right. So what is probability they're out of dress code given they're female? Well, that's going to redefine my world here to this circle. So it should be the 0.045 given the total here. So it's a probability that they're out of dress code and female over the probability of being female. So that's the same formula from the math chart. So it would be 0.045 over 0.47 plus 0.045, which would be 0.0874. Now, is there an association with out of dress code and female? I'm going to say yes. Why? There is one. Because these two probabilities are different. Probability of out of dress code given female is not the same as probability of out of dress code. And if they were kind of close, like I had 0.053 here or something like that, I would say, oh, they're probably independent. But they're significantly different, 5% all the way up to almost 9%. So that does mean that there's an association. Can I multiply the two probabilities, probability out of dress code times probability of female, to get both? Well, we know the and probability is here. And when I multiply these two, I get 0.0263. And why is that? They're not independent. There is an association. So if you ever want to show independence, show that the probabilities are roughly equal. If you want to show there's an association, show the probabilities are not the same. You basically just take the probability. This is a great way to show it right here. If I want to look at dress code and gender, and say out of dress code given a certain gender and just plain old out of dress code. Tree diagrams are a great way to look at probabilities that involve more than one attempt, especially if the probabilities change. It works really well. Much better than a formula, by the way. So I would argue, please try a table or a Venn diagram or a tree diagram before you automatically jump to a formula. Because when you do, your brain kind of turns off and just says, here's a number, instead of figuring out what's really going on. And tree diagrams almost always work unless they're really too big. So the first time a student takes the driving test, they pass 30% of the time. So they're not so good that first time. But afterwards, they're a little better, they practice a little more, and if they failed it, they're going to retake it, and they pass about 65% of the time. So our question is, What is the probability that it takes a student 3 attempts to pass? I really like a tree diagram for this because the probabilities change and I could really visually model the 3 attempts. So I'm going to do attempt 1, which means they could either pass the first time or fail, right? And the probability of passing is only 0.3 on this first attempt. That means failing is 0.7. In our case, we're trying to make it to 3 attempts. We've only done 1, so we'll try a second attempt. Does this part of the tree need another branch? No. Why would you take the driver's test again if you already passed it? I think that will only get you in trouble. Well, like, who knows? Maybe you could fail it. I have no idea. So if you fail it, then you're going to try it again, and maybe you'll pass it, or maybe you won't. But your probability of passing is much higher now. It's 0.65, whereas your probability of failing is 0.35. Then as we're trying to do 3 attempts, this is only 2, so we'll do the last attempt here. So we have pass or fail, and those numbers are the same. Okay, so we're trying to model the situation where it takes them 3 events. That means they would have to fail, fail, and then pass, because they're supposed to pass. Well, to figure out that probability of fail, fail, and then pass, you just multiply those probabilities together. The nice thing is, I don't have to worry so much about, oh, is that the given? It's sort of automatically the given when you do your trees and you change the branches to reflect that. See how this is now 0.35 instead of 0.7? This is a probability of failing given I failed the first time. This is probability of failing given I had already failed once before. So those numbers are already built into your tree. Multiply them out, and I get 0.159, or about 15.9% of the time we expect a student to need 3 attempts to pass. What is the probability it takes 2 or less attempts to pass? Well, you could be tempted to say, oh, 1 minus 0.159, but actually the kid could have failed a 3rd time. So it's easier to just look at the case of 2 or less attempts. So it's either 1 attempt, which is this one, or which would be probability of 0.3, or it's going to be 2 attempts, which is this one, fail then pass. So 0.7 times 0.65, that's almost half the time. So 0.455. So I just combine those 2 probabilities, and I get the probability that someone can pass in 2 attempts or less is 75.5%, or 0.755. Now we can also look at conditional probabilities with tree diagrams. So first of all, let's go ahead and create one. It has been estimated that 4% of students are using performance-enhancing drugs. A new drug test is 98% accurate at flagging performance-enhancing drug use among student athletes. It also has a false positive rate of 0.2%. Create a tree diagram to show the probabilities for each outcome. So first of all, it's easier. We know the probability of the outcome based on whether the student is taking drugs or not. So we're actually going to do the first part of our branch is going to be, are they a student taking drugs or are they clean? And we said about 4% of the students are taking the drugs. And then after that, we create the next outcome, which is either they get a positive or a negative drug test, and same if they're clean. We know about, and there's your outcomes. They're either taking the drugs with a positive outcome, they have the drugs with a negative outcome, they're clean with a positive drug test, and clean with a negative drug test. So there's my 0.04 finally, which means this is 0.96. And the probability that it's going to catch them if they are doing drugs is 0.98, which means the probability they'll miss is 0.02. The probability of a false positive, that means a positive test for a clean student, is 0.002. And so that means that the probability is 0.998 that a clean student will test negative as they should. So we can go ahead and calculate all of these probabilities by multiplying the branches. So drug and positive, I'm going to multiply the 0.04 times the 0.98, and there's my product. They're taking drugs and they get a false negative. That would be 0.04 times 0.02, so it's less than 0.08%, so it's very small. 0.96 times 0.002, so there's almost a 0.2% chance that someone who's clean is clean and gets a positive drug test. I have to be careful how I say that. And then clean and a negative drug test is 0.96 times 0.998. And there's the probability there. You can double check these by adding them all up and making sure they add up to 100% or 1. So the question is, what's the probability of a false positive? I'm sorry, a false negative. So that would be someone who takes drugs and gets a negative result. That's just the product along this path, or 0.0008 or 0.08%. What's the probability of a false positive? Well, that would be this path right here, which means it'd be this number right there. Now, the interesting part is we can look at conditional probabilities. If someone tested positive for drugs, what do you think is the probability they're taking drugs? A lot of times students say, well, it's probably 98%. Is it though? So let's go ahead and take a look. It might not be that different. So probability that they are using a performance, given that they tested positive, the probability they actually are using drugs. So that's taking drugs given they tested positive. So that would be drugs and positive over the probability of positive. So the drugs and positive, that's 0.0392. Only 2 of these outcomes have a positive result, so I add both of them up. The 0.0392 right here, that's drugs and positive, and then the 0.00192. So it doesn't look like it's going to change it very much, and in reality, it's almost 98%, but it's not actually. It is a little different, which means, by the way, just for the fun of it, what's the probability, if they get a positive drug test, what's the probability they're clean? Well, I could use the same formula, 0.00192, over the sum of the 2 positives, and I get 0.047, which kind of makes sense. You have the people who test positive, about 95% of them did use the drug, but you actually have about 5% of them which didn't use a drug, which is interesting. If you look at this number right here, let me go ahead and change colors. Color. So if you look at this number right here, 5%, you might have thought that only 0.2% of people who tested positive were innocent, but it's actually a bit higher. And that has to do with the fact that these populations are not exactly the same, and you have very small percentages. So we can often see this effect. So in conclusion, there's some strategies I want to go over again. Make sure you try one of these first before jumping straight to a formula. Even when I was using that conditional probability formula, I still had a sample tree or a tree diagram. So first of all, you can always do simulation, all right? Kind of like we did for the 1 in 6 game. You can do a sample space, especially for equally likely outcomes. Venn diagrams work nicely. Two-way tables are a great tool. And then tree diagrams. So there are multiple ways to look at your probability problems.